Hi everyone, and a very warm welcome to today's Oxford Discrete Maths and Probability seminar. So we're going to get started with Igor Kortchemski, who's joining us from Ecole Polytechnique. It's a huge pleasure to have Igor here, and he's going to talk to us about the geometry of random minimal factorizations of a long cycle. As usual, if you have any questions, please ask them in the chat, and Alex and I will sort of curate them if we can. Over to you, Igor. Thanks.
Yeah, thanks a lot for the invitation. I'm very happy to give this virtual seminar on a joint work with Valentin Féray concerning the geometry of random minimal factorizations of a long cycle. And I'll first start with the first part concerning random triangulations of polygons, which seemingly has nothing to do with random minimal factorizations of a long cycle, which is in part true, but there are still some similarities, some common ideas, and a connection that will appear later on. So it will be a gentle introduction to minimal factorizations. I will state the model and our main result and give some glimpses of the main steps of the proof. Let's start with triangulations. We will consider polygons and triangulations of polygons. So here is an example with a polygon with 10 vertices. You draw diagonals which cannot intersect, and you draw as many as possible to get triangulations. So it's well known that there is a Catalan number of them. And the question I ask is, what does a large triangulation look like? Of course, there are many of them, but if you put all of them in a bag and with your innocent hand take one of them at random, what does it look like? And we fix the vertices to be the n roots of unity so that the polygons stay in the same region. So here are some simulations with an increasing number of vertices. Here is, I don't know, how many vertices are there? 20, something like that, I don't know. Then I increase the number of vertices, and here is one simulation of a uniform triangulation of a large polygon. And the number of vertices grow. These objects are random, and as n increases, you see the circle appearing, which is of course natural as the n roots of unity approach the circle. And it seems that there is some continuous random triangulation appearing. And Aldous proved 26 years ago that this is indeed the case. And to prove a convergence result, we first need to define a space in which all these objects live. So what space do we consider for these objects? And Aldous's idea was to view them really as drawings in the plane, as, formally speaking, compact subsets of the unit disk equipped with a certain distance, which measures how far apart are two compact subsets of the unit disk. And this distance is based on the Hausdorff distance, which I recall now. It allows to define how far apart are two subsets of a same metric space based on their R neighborhoods. And here is the formal definition. We look at the smallest enlargement of y and of x, such that x is in the R enlargement of y and y is in the R enlargement of x. So you do an enlargement like that, and you take the smallest of these numbers. And if you look at compact subsets of the closed unit disk, this is indeed a distance, which makes the space Polish, so very nice to do probability inside. And Aldous showed that if Tn is a random uniform triangulation of the polygon with n vertices, then we have convergence in distribution to a certain random object, which is a random compact subset of the unit disk. And this convergence in distribution holds for the Hausdorff distance on all compact subsets of the unit disk. So as a drawing, a random triangulation appears in the limit. Here is a simulation of it. And it is a triangulation in the sense that the complement of the compact subset is a union of triangles. And YL of E, because it is coded by the Brownian excursion E, and for this reason it's called the Brownian triangulation. And I will explain in a few minutes how this is coded by the Brownian triangulation. But before that, maybe a nice sort of connected combinatorial consequence of this abstract convergence is concerning the length of the longest chord of the Brownian triangulation. If we do the change of variable to measure lengths not in the Euclidean way, but by the proportion of the angle intercepted by the chord. So for example, in this example, the length, angular length is theta equal 1/4. Then the length of the longest chord of the Brownian triangulation is a probability measure with this density. And it was obtained by Aldous by doing a computation directly using the Brownian triangulation. And it was also obtained by De Vrooy, Flageolet, Hurtado, Noy, and Steiger by explicitly computing the distribution of the longest chord in Tn, and passing to the limit, we get the length of the longest chord of the Brownian triangulation. So in one case, it was made by a computation in the continuous world. In the other case, it was obtained as a corollary of this convergence, and using the fact that the longest chord is a continuous functional for the Hausdorff distance. And this quantity will appear later when studying random minimal factorizations. So why the Brownian triangulation? How is the Brownian triangulation coded from Brownian excursion? Consider a Brownian excursion, which is informally speaking Brownian motion, which you condition to come back at 0 at time 1 and to be non-negative in between. And once we have this excursion, in a deterministic way, we construct a triangulation by considering all tunnels, meaning, let's see, so you here and here, you have 2 points under the excursion which look at each other. You look at their times. It gives 2 points on 0, 1. And these 2 points on 0, 1 give you 2 points on their circle. And you do this for all tunnels. And since you have an excursion, it's not very difficult to check that the chords are indeed non-crossing, which is maybe not clear at first sight, but it's not very difficult to check. And you get a continuous triangulation. And since the Brownian excursion you started with was random, you get a random triangulation of the unit disk. So this is the definition of the Brownian triangulation. So why this construction? Why do random triangulations converge to this Brownian triangulation with a Brownian excursion popping up? There are essentially 2 reasons. The first reason is that behind the triangulations there are trees. So behind random triangulations there are random trees, and behind random trees there is the Brownian excursion. So here the dual of a triangulation is a binary tree. This is very natural. And something which is important to keep in mind is that big chords correspond to big subtrees. For example, if we look at this chord, it splits the tree into two big subtrees. So big chords are in sort of correspondence with big subtrees. Now, what is the connection between random trees and the Brownian excursion? The reason is that we can code trees by sort of excursion type functions. And when the trees are sufficiently chosen randomly in a nice way, the corresponding excursions will scale to the Brownian excursion. So more formally, if we have a plain tree like this, we start by labeling it empty set the root, 1, 2, the children of the root, 1, 1, the first child of 1, 1, 2, the second child of 1, 1, 3, third child of 1, 1, 4, fourth child of 1, and so on. So this is the so-called lexicographical order. Just the labeling of the vertices. And once we have the labeling of these vertices, we can consider the lexicographical order on these labels, which defines a natural order on the vertices of the tree, which is called the depth first search. And once we have this depth first search, we code the tree by the Lukasiewicz path. So how does it go? We start from 0, and then we explore one by one the vertices of the tree in lexicographical order, and we make a jump, the jump being the number of children of the vertex where we are, -1. Here, for example, the root has 2 children, so we make a jump of size 2 minus 1 equal 1. And we move to this next vertex, which has 4 children, so we make a jump of size 3. This vertex, the next one, has 0 children, so we make a jump of size -1. And so on. And we get an excursion type function, which bijectively codes the tree. And when the trees are Bienaymé-Galton-Watson trees, associated is a sort of conditioned random walk, but I don't want to enter too much details. But before considering random objects, there is a deterministic correspondence between tunnels and subtrees, which is reminiscent, of course, of what was before. For example, here at the vertex 5, we have this subtree, which corresponds to this Lukasiewicz path. So in this coding, we have a correspondence between tunnels and subtrees. And in the case of random triangulations, we have uniform binary trees, which correspond to a very nice path. And in this case, the scaling limit of the Lukasiewicz path of the dual of uniform triangulation is the Brownian excursion. And this is just Donskier's invariance principle in its conditioned form. So I don't want to enter too much details, but just to highlight the main ideas. But the main, there are essentially 2 main ideas. The first one is that tunnels correspond to big chords, and we can read tunnels on the excursion coding the trees. Don't hesitate if you have questions on this part on random triangulations. Okay, so let's continue with the model of minimal factorizations with the 2 questions. The first question, how many are there? And the second question, what does a large typical minimal factorization look like? Let me first define what a minimal factorization is. We will consider a long cycle in the symmetric group with n elements, 1, 2, 3 up to n. So it's a permutation sending 1 to 2, 2 to 3, and so on. And we factorize this long cycle using as less transpositions as possible. So it's not very difficult to see that you need at least n-1 transpositions. So we consider all factorizations into exactly n-1 transpositions. So this is called the minimal factorization of the cycle into transpositions. So first question, how many are there? For example, if we multiply to simplify or complexify, it depends, things from left to right, it's not very difficult to check that for n equal 3, you have exactly 3 such factorizations. And in general, it is known since Dinesh that there are precisely n to the power n minus 2 such factorizations. The first proof was not bijective, but then there were found nice bijections with Cayley trees, with parking functions. There's quite a rich combinatorial structure behind. And the question we were interested in with Valentin was the following. For n very large, what does a typical minimal factorization look like? Before being a bit more precise simulation, for n equals 60, here numeration is not between 1 and 60, but between minus 29 and 30 for a bit practical reasons. And so let's see if I can make this work. So what color? Blue, no, red. If we start from 0, we look, we go from left to right. When we go from left to right, we read transpositions. Sometimes here 0 is not affected by transpositions. Sometimes it is affected. And if we look at the trajectory of 0, we should end at 1. So 0 gets sent to 1, 1 gets sent to 2, and so on. So this is an example of a minimal factorization of the 60 cycle. And you see that sometimes you have small transpositions. For example, here. Sometimes you have quite large ones, for example, here. And here you see also a large one here, a large one here, and a large one here, a large one here, a large one here. And all these seem to be nearly more or less the same. Okay, so we were interested in understanding a bit this structure, typically what happens. And we had some motivations in mind. First, there is a very rich combinatorial structure of minimal factorizations, which is one of the motivations in studying this model. There is a connection with enumerative geometry through Hurwitz numbers and Hurwitz formula. It can be seen as a general model of random product of random transpositions, a sort of a random walk on the symmetry group. One of the motivations was also come from the random sorting network, the model studied by Angel, Olroyd, Romik, and Virag, which is a different type of factorizations using different type of transpositions of a different permutation, which is a very different class. And it turns out also that this model has a rich probabilistic structure with connections with the additive coalescence and the Aldous-Pitman fragmentation of the CRT. This was explored by Paul Thévenin. And to obtain limit theorems on random large minimal factorizations of the long cycle, well, we need to find a space for minimal factorizations. And here is the connection with the first part. We will also view them as drawings, as compact subsets of the unit disk. Now I will explain how, since this seems maybe a bit strange. So to do this, we actually associate to minimal factorization compact subset of the unit disk in two ways. And each way, we will read first the first transposition, then the first two transpositions, the first three transpositions, and so on. So I will directly explain this on an example. It will be a bit more clear. So we read the first transposition, 1, 3. Here we draw the chord 1, 3 in both cases. Then we read the second transposition, 6, 12. In the left, we will always draw chords with endpoints, the numbers we read in the transposition. But for the right, the figure on the right, we do the product, the partial product of the transpositions we have read so far. We factor them into product of disjoint cycles, and we draw the convex envelope of the cycles. So for example, if we read the third transposition 1, 5, on the left, we add the chord 1, 5, but on the right, to find out what is the drawing on the right, we do the product of the first three transpositions. We get this permutation, and we draw 1, 3, 5, 6, 12. So here I continue. So there are some interesting properties that seem to appear. Well, first, the chords are non-crossing. The cycles which appear in the partial products are always formed by non-decreasing, increasing numbers. And in the end, in this example, on the right, we get the polygon, which is normal because the product is the cycle. And on the left, we get a tree, which is non-crossing in the sense that the chords are non-crossing. And it turns out that this is not a coincidence. In general, it is possible to show that the chords are always non-crossing. That actually, once we have the figure on the left, we can get the figure on the right just by considering the convex hulls of the connected components. So the cycles of the partial product are just the connected components of the forests on the left. However, we cannot just go from the right to the left. And as we read more and more transpositions, blocks disappear on the right. As we read one more transposition, we get one less block. And this is something which comes from the fact that we are working with minimal factorizations, meaning that we want to factor the n cycle using as less transpositions as possible. These are some combinatorial properties which are not that difficult to check. Okay, so now going to random minimal factorizations. What happens if we read transpositions one after the other? So the question, or maybe the thing we were interested in with Valentin, was to find, in the beginning, we wanted to know if there was a phase transition, meaning that if we read one after the other, the n-1 transpositions, is there some, at some point, is there a scale at which appear large transpositions or large chords? Is there is there a phase transition? Is there a critical window? What happens? Or maybe maybe you read big transpositions right in the beginning. Maybe in the beginning you read small transpositions, that after some point you read large transpositions. This was basically the question we were interested in. So we did some simulations, and we first thought that maybe rather naturally a phase transition should appear when we read a positive proportion of transpositions. So here, n equal 20,000, and on the left you will see the increasing forest, and on the right the non-crossing partitions. So here C is equal to 0.2. So here nothing happens. You see a triangulation. And at the end, as expected, on the right, we get the circle, and on the left, nothing changes because on the left, everything is increasing. So here, if I show again the film, what this simulation suggests is that at the scale n, we're already in a sort of stationary phase. Everything has already happened before. And it turns out that the correct scaling, the factor, actually the time at which the scaling, the phase transition appears is when we have read actually square root n transpositions. So here is a simulation in this scaling. In this scaling, you see chords appearing one after the other. When C goes from 0 to 10. And the result we have shown with Valentin is one-dimensional convergence, one-dimensional marginal convergence for a fixed value of C. So more precisely, there are 4 regimes for a uniform minimal factorization of length n when we have read kn transpositions. The first regime is little o of square root n. We have not read, we read less than square root n transposition. Second regime, we read of order square root n transpositions. Third regime, we are in the bulk. We have read much more than square root n transpositions, but not all of them. Meaning that the number of transpositions which are left to read is big compared to square root n. And last regime, it's a sort of the symmetric of the second one. It's when we have read nearly all of them. And we obtain in the first case a joint convergence here to the circle. This just tells us that if Kn is little o of square root n, the length of the longest transposition tends to 0 in probability. No large transpositions have appeared. In the second regime, there is a random compact subset, which depends on C, such that the non-crossing forest and the non-crossing partition converges to the same random compact subset. This explains the fact that in the previous simulation, we saw the same picture on the left and on the right. In the stationary phase, in the bulk phase, we have joint convergence to the Brownian triangulation. This is the triangulation which didn't move in the first simulation when we were at the scale n. And in the last regime, the non-crossing forest still is the Brownian triangulation, but the non-crossing partition sort of decreases back to the circle going through LC. So this is our main result. And I will describe just a bit later what is LC. Are there any questions on the statement of this result? Okay, so what are the limiting objects? Well, L0 is the unit circle. L infinity, this L of E, is Aldous' Brownian triangulation, which is the Brownian triangulation coded by the Brownian excursion by looking at all the tunnels. And we can explicitly describe the law of LC. It turns out that it's a lamination, meaning that it's a closed, so compact subset of the closed unit disk made of non-crossing chords, but the faces are not triangles anymore. And the fact that it's not triangles anymore is essentially connected to the fact that it's coded by a process, excursion type process, but which is not continuous. It has jumps, and jumps are in correspondence with faces. And the method the lamination is obtained from the excursion is still by drawing essentially all the tunnels. And interpretation for the constant C. Well, it's the constant C. It appears here. It just says that if we read C times the square root n transpositions, we get LC in the limit. So C, if it's a sort of a time parameter, which just tells you how many transpositions you read. And this Levy process, we explicitly find it. We compute explicitly its Laplace exponent.
Igor, can you just explain again how you get the lamination from the Levy process?
Yeah, or by the.
So it's just literally, again, parts of the excursion that sort of touch
Yes.
a line.
Yeah, but yeah, but here I'm being a bit imprecise because here you have a jump. So you have to be a bit careful with the moments of jumps, but it's essentially just, again, looking points, for example, under the excursion, which see each other, but maybe, I should say that, for example, here, when you have a jump, you put vertical walls so that, for example, these two points are not looking at each other. So this is not a tunnel. Because when you make jumps, you draw vertical barriers.
Thanks.
Maybe I can try to write a formula. So we draw, let's say that ST is a tunnel if XT is the smallest U greater than S, such that XT, something like that. Oh. Like that.
Thanks.
And an interesting corollary, a combinatorial consequence of this convergence, is that if we look at the sort of size or width of a transposition, defined in this way, then the size of a transposition, it's essentially its length drawn in the circle. So a consequence of the previous convergence is that if we read C times square root n transpositions, and we look at the sort of maximal size of the transposition we have read up to time kn, then it's of order n, at least when C is positive, and we converge in distribution to a certain random variable, which is of the length of the maximal chord of LC. Length, I mean angular length. For C equals 0, L0 is just 0, and L infinity is the length of the maximal chord of the Brownian triangulation, which I showed you explicitly before. So this result allows you to understand the behavior of the largest size of a transposition, which you have read when reading one after the other the transpositions of a uniform minimal factorization of the n cycle. So it's a nice combinatorial result. And it is quite surprising that the limit is the same for log n square root n or kn equal n minus 1. It means that if you're interested in the sort of largest transposition you get, you have already seen it if you have read way more than square root n transpositions. But after log n square root n up to time n minus 1, there are still a lot of transpositions you read. Of course, they will be all different, but the size of the longest one will not change. So this is maybe a drawing to understand that. Is that here you see that you have a large transposition here, and you have large transpositions here, 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 but they are very close to the first one. Okay. Okay, now I'd like to give just the main steps of the proof. How do we identify LC? Why is this? There's this Levy process, excursion type process with jumps appearing. So I'll explain the main ideas in the regime C square root n. The first step is to explicitly identify the law of the non-crossing partitions. So this is the advantage of working with non-crossing partitions. You may think that it's more natural to work with the non-crossing forests because they are increasing. You add chords one after the other. You have a monotonicity property, which is very nice. So that's true. But the disadvantage of the non-crossing forests is that their law is not explicit. It's very complicated. So this is why, essentially, even to understand the law of non-crossing forests, we go through the non-crossing partitions whose law is explicit. Then we will code this non-crossing partitions by random trees, which will be a bit more complicated than in the case of triangulations, because it will be not one type trees, but two type trees, and not size conditioned trees, but two size conditioned trees. Then we study these trees and we conclude. So what is the law of the non-crossing partition once we have read K transpositions? So okay, what is this thing? We multiply the k first transpositions. This is a permutation. We factor it in the product of cycles, and cycles give blocks. And these blocks are non-crossing. They form a non-crossing partition. And here we take a non-crossing partitions with n minus k blocks, because when we read k transpositions, we always get n minus k blocks for the non-crossing partition. And the law involves the Corollary complement of a non-crossing partition. So what is the Corollary complement? So this is an example of a non-crossing partition. You put new dots which correspond to the polygon which you rotate just a bit, and you look at the polygon you can form in the blank spaces left by your non-crossing partition. And this gives you the Corollary complement. So you have a non-crossing partition, its Corollary complement, and then the law of the non-crossing partition you get after reading the first k transpositions is explicit. There's some factor which depends on k and n, and there's a product on the blocks of the non-crossing partition and on the blocks on the Corollary complement. And the things involved are just the sizes of the blocks. And this is not very difficult to prove. This is behind is the fact that the number of minimal factorizations of a cycle is explicit. You recognize this this formula, and these factors are essentially a shuffling combinatorial factor, which tells you that if you take two minimal factorizations of two cycles with disjoint support, then you can intertwine the different transpositions among them. This is a combinatorial flavor result. Where is my mouse? Oh, it's here. Okay, and this result also allows us to understand why the phase transition is at square root n. Because by taking k equal 1, well, you get explicitly the law of the first transposition. And you can compute the probability that the size of the first transposition is I. So it's explicit. And when I and n are large, you get something like that. So the probability that the size of the first transposition is I has a, you say, power, sort of power tail behavior. And if you believe or assume that the transpositions you read one after the other in the beginning are IID, how many transpositions should you read so that the maximum of them, if they have this behavior, the maximum is of order n? Well, it's exactly square root n. So this explains the square root n behavior. And once we have this, we can code this random non-crossing partitions by random, by type, by condition Bienaymé-Galton-Watson trees? Well, first, if we have a non-crossing partition, we can code it by a two-type tree, like this. Here, there are naturally two types, one type with the blocks, one type with the blank spaces, which actually correspond to the blocks of the Corollary complement. And in this random tree, the weight we had for, if I go back, you see that the weights here involve sizes, just sizes of the blocks, and sizes of the blocks are just degrees. So you have weights corresponding to degrees, red degrees, blue degrees. So behind there is a model of, if you want, combinatorially speaking, of simply generated trees, where you have weights depending on the degrees, but there are two types, red, blue, and the number of red vertices is fixed and the number of blue vertices are fixed. And this is a different conditioning than those considered for limits of multi-type Bienaymé-Galton-Watson trees, where generally either the total size is fixed or just the size of one type is fixed. The reason is that, just in a few words, that in the conditionings previously considered, the reduced trees, the reduced blue tree or the reduced red tree, are Bienaymé-Galton-Watson trees. Here in this bitype conditioning, it's not the case anymore. So it's you have to be more careful. And a major part of our work actually is devoted to developing a machinery to study the limits of such random trees. We essentially extend the Lukasiewicz coding to a two-dimensional random walk coding, which we analyze. And also, since the number of vertices are fixed and which are not necessarily a typical one, we also have to do some exponential tiltings. So the offspring distributions involved will depend on n. So we have bitype, biconditioned Bienaymé-Galton-Watson trees with offspring distributions that depend on the size. So it's rather involved, but I hope that the main idea is clear. So to conclude, we have shown the convergence of the one-dimensional marginal distributions for C fixed. And also one of our goals was to develop in parallel machinery to study multi-type Bienaymé-Galton-Watson tree, multi-type, multi-condition Bienaymé-Galton-Watson tree, which is of independent interest. And afterwards, Paul Thévenin, who is a former PhD student of mine, extended the one-dimensional convergence to a process convergence. So he really established that there is a sort of film going on when C increases at a scale square root n. In particular, he coupled the different LCs on a common probability space and proved convergence in the space of lamination value, the Cadillac processes, using different tools in connections with percolation on random trees and Aldous Pitman fragmentation of the CRT. A sort of a planar version of the Aldous Pitman fragmentation. There are still quite of work to do because there's a very rich structure in these factorization models and very few probabilistic results. So thanks for your attention.
Thank you very much, Igor. Are there any questions? So I think at the moment I've got it so that people can unmute themselves, but I think it's probably easiest if you nonetheless write in the chat or raise your hand if you have a question to ask, and I'll perhaps I can get us started. So you mentioned that you've had to work quite hard in order to build up this new machinery for these two-type trees. Are there other applications of that machinery that you can now sort of get at, or is it for the moment something which is sort of waiting to be used a bit more?
So a bit indirectly, so it's maybe so there in this machinery there are several things involved. There is the fact that we have several types and conditioning on several types, and the fact that the offspring distributions depend on n. So the fact that the offspring distributions depend on n, this is useful for something that something we're doing with Michael Mazoun and Cyril Marzouk, where we are studying random maps, Boltzmann planar maps with two-type conditioning. Usually we study planar maps by conditioning them on a total number of faces or total number of vertices. And here we study a double conditioning, fixed number of vertices and, for example, fixed number of faces. For example, take a uniform planar map with n faces and n to some power a vertices. What are the scaling limits? So to study this question, this machinery is quite useful.
Thanks, that's great. It was reminding me of some of these map models where you have sort of colors and interesting conditioning. Thanks. Does anybody else have any other questions?
Yeah, in this Boltzmann planar map case, it's a bit nicer because through this Jansson-Stefansson bijection, one type, you can map actually the two-type model to a one-type model, and you have to understand jointly vertices and leaves. So it's a bit, the combinatorial structure is a bit simpler.
Mm-hmm. And maybe a question of a different flavor. What happens if rather than taking transpositions, I take sort of factorizations into different sorts of kind of smaller units?
Yeah, so maybe I can write it here. So minimal factorizations, but so still minimal, but you allow more general cycles, not necessarily transpositions. You can allow, for example, 3 cycles and so on into more general with more general cycles. This is something that Paul has studied. You can even put weights, even with a weight, for example, W of k, if you use for using k cycle. Mm-hmm. For example, the model of minimal factorizations into transpositions, it amounts to taking the weights to be just the indicator k equal to 2. So you obtain very general results in this framework. And in a different direction, if you don't want minimal factorizations anymore, but you allow a small excess, this is also something that Paul, Baptiste, Louf, and Valentin Féray are studying to understand what happens in this case. So do you still get
strange situation?
Yeah, do you still get laminations? Do you get laminations, but maybe you add new chords which will cross, which will add crossing? So this is something also which is which has some nice things going on.
There's a question from Victor Miller in the chat. Does this have any generalizations to other Coxeter groups?
Not to my knowledge. Yeah, it would be.
And then Matthias, feel free to unmute yourself. He can't apparently. Let me see if I can do that. There you go. You should be able to speak now.
Okay, thank you. Yes, very, very nice talk. Very interesting structures that that you've put together here. So I'm particularly interested in these excursions that you've drawn, these sort of Lukasiewicz paths. If I understood correctly, they are sort of Lévy processes, but they are still returning to zero at time 1, although they are not stable Lévy processes. So how exactly does the conditioning work here?
So this is some, just to define the object. So these are general results by Chaumont, Uribe, Bravo, which define Lévy bridges. A Lévy bridge just conditioned to return to 0 at time 1. And then you do a Vervat transformation.
So
there are
there's
some...
no self-similarity in these?
No. No, it's
not
not
the
indeed.
Same Lévy process which drives all of these different excursions, because what you seem to be using is that that what you have up there in a sort of above one of your tunnels is in some sense a small copy of the whole thing, but not in the sort of scaling sense, but in a sort of conditioning the same Lévy process sense. Then is it?
Yeah. So what happens is that actually this Lévy process is just the scaling limit of the reduced, I never know, red or blue tree here. So you have this two-type tree. You take the reduced red tree, you take its Lukasiewicz path, and this will give you this this Lévy process.
Mm-hmm.
But yeah, so maybe another way of another maybe way of describing it, which is a bit connected to what Paul did, is if you take the CRT, let's draw it in a plain way, then you take your chainsaw and you make rain chainsaws on your tree. So if you want, you put, if L is the length measure on your CRT, you take Poissonian rain with intensity C dl.
Yes, this is the oldest Pitman fragmentation.
Yeah, that's right. And then what you do is that you look at the connected components. So here, this is, and you look at the tree of components. So one connected component is one vertex. Here you have one connected component. Here is one. 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 And then you look at the. So you get this. You look at how the components are glued one with each other, and essentially, this tree you get, its Lukasiewicz path is the Lévy process before.
So each component corresponds to a jump in the Lévy process.
Not exactly a component. Yeah, that's right. Yeah, that's right. Components correspond to jumps, and the largest the jump is, the more components are attached to the component.
And does this, what you've just described, does that describe the dynamics as C varies in some sense? That you increase the intensity of your process?
Yeah, that's right. So the way Paul couples this is that he does a planar version of this, a la Abraham Serlet. You take a Brownian excursion and you make rain under the excursion, which a certain intensity, which will depend essentially on the, if you have a point T, you have dt gt. So the intensity will be, roughly speaking, C divided by maybe a 2, something like that. You take a Poissonian rain under the Brownian excursion with this intensity, and when you fold things up, you get the Aldous-Pitman fragmentation on the CRT, and here you couple this in an increasing way as C increases. So you have one Brownian excursion with more and more points under the excursion. And when you draw a point under the excursion, you draw a chord. So this allows to couple the LCs together. But for the moment, it's an open question to couple the Levy excursions together. It would be nice to couple the Levy excursions together.
Well, thank you. That's very interesting.
But yeah, but that's I mean, there are this is also connected with this other representation of the additive coalescence by Bertoin of Brownian excursion with a varying drift. So I mean, yeah, there's connections with
Good.
different things, but for the moment, not 100% understood.
Thanks.
Great. Thanks very much. I think that's all the questions. So what I'm going to do is I'm going to stop recording and I'm going to propose that